Welcome to this explainer. Today, we're diving straight into a truly fascinating bridge in modern mathematics. We are going to explore exactly how the Adelic Langlands program takes one of the most notoriously difficult discrete combinatorial puzzles out there, the Bounded Burnside Problem, and totally translates it into the flowing, continuous language of spectral geometry. Because honestly, sometimes mapping discrete, seemingly impossible problems to continuous geometries is literally the most powerful tool we have in our arsenal. If you love seeing rigid algebraic structures suddenly melt into elegant geometric landscapes, you are definitely in for a treat today.
Okay, let's dive into this. And hey, while the upcoming equations do get pretty deep, we have a very clear 6-step path for our tutorial today. 1. The Bounded Burnside Problem. 2. Words to spectral geometry. 3. The arithmetic engine. 4. Proving finite bounded growth. 5. The infinite divergence tower. And finally, 6. The geometric spectral resolution.
Section 1. The Bounded Burnside Problem.
So it starts with what is essentially a discrete combinatorial nightmare. The Bounded Burnside Problem asks a deceptively simple question. It asks, if you have a finitely generated group, and every single element satisfies the power relation x to the power of d equals 1, does that group absolutely have to be finite? For decades, mathematicians wrestled with this. It was treated as an intractable, discrete tree of words. Now, for small exponents, yeah, sure, it's finite. But for really large ones, it turns into a sprawling, infinite beast.
But here is where the whole paradigm completely shifts. The Adelic Langlands program acts as a miraculous mathematical translator. Instead of fighting our way through an impossible branching tree of discrete words, we actually reinterpret that simple exponent condition into a universal nilpotent trace constraint. We're taking the entire problem and shifting it into spectral geometric data on a global automorphic representation. It's a massive leap.
Section 2. Words to spectral geometry.
In this completely new framework, finiteness is mathematically equivalent to algebraic support on the Hitchin moduli space. Think about it structurally. A finite group neatly collapses into a finite direct sum of matrix algebras. Those are represented by isolated bounded algebraic points. But what if the group is infinite? Well, it just spreads endlessly. It forms an infinite-dimensional, non-terminating fractal distribution straight across the Hitchin base.
Now, to get from those discrete words all the way to that continuous fractal geometry, we follow a snappy 4-step procedural roadmap. First off, we map abstract word length to a scaling variable. Second, we use the Selberg trace formula to compute the geometric volume of the spectrum. Third, we test global functional stability using local root numbers. And finally, step 4, we synthesize our thresholds to see if the spectrum is discrete or continuous. So now that we have our roadmap, let's really look under the hood.
Section 3. The arithmetic engine.
The absolute crucial point here is how we handle the exponent condition without losing all that precious non-abelian information. We evaluate it under local Langlands parameters at specific primes. Focusing on the local factor equation here, the parameter essentially dictates that the eigenvalues of the representation image must be d-roots of unity. Now, if you've ever wrestled with unramified states before, you know just how crucial this next part is. The Frobenius action, right there in the middle of the determinant, evaluates those unramified states. But watch out, because that standard determinant collapses entirely if the active dimensions get rigidly absorbed into local phase shifts.
Let's zoom out for a second and see how this builds into the global picture. What we have is our universal arithmetic syndrome coordinator. This global functional equation acts as an exact modularity check across the entire system. And here is the ultimate test. If a pair of generators allows the group to be infinite, the continuous cycles of the complex prime torus must somehow absorb an infinite cascade of local Swan conductors. If they can't manage that, the whole function just shatters.
And that brings us to the critical bifurcation of this explainer: tame factorization versus wild ramification. If the prime doesn't divide our exponent, the action is unramified, mapping beautifully and smoothly to Dirichlet functions. The Swan conductor stays totally stable. But if the prime does divide the exponent, the valuation matrix collapses, the inertia group acts wildly. And if our group is infinite, this wild ramification triggers an unstoppable exponential cascade divergence.
Section 4. Proving finite bounded growth.
Let's ground this arithmetic in a very specific case study. Let's prove bounded growth when our exponent d equals exactly 3. For d equals 3, let's look first at primes that are not 3. This is the tame, unramified sector. Notice the multiplicity variables in this formula. The variable a sub p actually counts the trivial eigenvalues, while b sub p gathers the matching conjugate pairs of the non-trivial third roots of unity. Because everything perfectly pairs off, this entire unramified sector cleanly factorizes into predictable, highly stable components. Absolutely zero unbounded growth here.
But what about the wildly ramified prime where p equals 3? Well, this is the sheer magic of finite groups. The equation completely collapses to a finite phase shift. Look closely at that flat polynomial scaling at the end, 3 to the power of negative 2s plus 1. Because the wild ramification is strictly confined and scales as a flat polynomial, it only ever generates a finite number of exceptional phase shifts. The global product converges smoothly. Mathematically speaking, it definitively proves the group cannot grow into an infinite tower.
Section 5. The Infinite Divergence Tower. Now, let's dramatically contrast that finite elegance by escalating the situation. What happens when the exponent is, say, 8,000 or greater? For large, even exponents, infinite word generation builds what is known in the field as a Novikov-Adanian word tower. The power relation entirely fails to truncate the lower central series. Instead, generating longer words forces a cascading, infinite sequence of wildly ramified Galois extensions over the two-adic field. It just plunges into deeper and deeper ramification breaks. There is no bottom.
And this wildly unstable tower triggers an absolute catastrophic explosion in the local Swan conductor. Let's tour this growth law equation. We have k times n times mu to the power of n. So where does this massive divergence come from? It's a combination of dimension inflation, where the syzygy matrix grows exponentially via the Cayley graph, and filtration depth extension, where deep wild ramification breaks scale linearly. They violently combine. This isn't just standard growth, folks. It is an unavoidable exponential explosion.
And this brilliantly illustrates the ultimate consequence of all this. When you take that exponentially blowing up Swan conductor and feed it right back into our global partition function, the continuous cycles of the prime torus are completely overwhelmed by phase delocalization. The function naturally develops a boundary of essential singularities right at the critical edge of s equals 1/2. The holographic boundary literally, physically shatters into fractal chaos. This is the exact undeniable spectral fingerprint of an infinite group.
Section 6. The Geometric Spectral Resolution.
Let's zoom back out and conceptually resolve this whole thing by tying it back to the global algebraic structures. We do this through a really elegant, three-step algebraic quenching process. We map our abstract, discrete constraint, that word flow generated by the nilpotent monodromy operator, directly to a continuous field. The strict periodic relation, w to the power of d equals 1, acts as a quenching operator. Over a field of characteristic 0, it completely annihilates the non-abelian residue, forcing that nilpotent monodromy matrix to physically vanish over the unramified channels.
So what does that actually mean geometrically? It means closed periodic words map identically to highest weight vectors in the SL2C spectrum. Understanding the state diagram here, the step-up operator x plus pushes us along the orbit. But because our monodromy vanished, x plus acting on the period vectors simply equals 0. The highest weight vector represents perfect S-duality balance. It's the exact equilibrium point where discrete word expansion is perfectly locked and bounded by the strict mathematical period d.
So, to summarize the core structural duality we've been exploring today, for finite groups, the highest weight bounds force a closed, very small integer state, which yields a clean product with finite poles, but for infinite groups, generators crosstalk. The nilpotent operator completely fails to collapse, the ladder of states becomes this infinite, continuous spectrum, and the local factor entirely diverges. The impossible discrete combinatorial problem is ultimately solved purely through these geometric spectral limits.
Which leaves us with a truly profound thought to end on. If the Adelic Langlands program can take the chaotic, infinitely branching trees of the Burnside problem and resolve them into beautifully structured spectral geometries, what other impossible combinatorial mysteries are out there right now, just waiting for the right geometric lens to reveal their elegant, continuous solutions? It's something to think about. Keep exploring, keep questioning, and I'll see you in the next explainer.